Okay, this is quiz version 2, and of course this is all similar stuff, but the questions are different, so I thought I would make a separate video just so y'all that took it in the afternoon would have something specific to you rather than having to glean your answers from the other one. Okay, so we got the same set of equations as version 1 did, and we see here that we have an AC motor. We're told it has 3 phases of input AC electricity, so 1, 2, and 3, each pair of electromagnets getting a phase. And the frequency of the AC electricity is 50 hertz. So those 2 pieces of information are particularly important. Now, part A asks us a pretty straightforward question. What kind of AC motor is this? Okay, in terms of the ones that we've covered. And the answer to this is synchronous. And the reason we know, permanent magnet on the rotor. Okay, if you got a permanent magnet and nothing else, okay, well, then that has to be a synchronous motor. There's going to be no slip or no real detectable slip. There's no reason for slip because we don't need to induce any electricity onto the rotor, and we're just following the rotating magnetic field here with our permanent magnet. Okay, so that's what a synchronous motor looks like, and that's what we would have. It's worth noting that you could also have an electromagnet here, but you'd have to power that somehow. It's like you could simulate a permanent magnet by having an electromagnet and then having some sort of brushed connection that would route the current on there and create the north and south. But the effect would be the same. You get a synchronous motor. All right. So if the permanent magnet was replaced with a squirrel cage rotor and you measured the rotational speed of the rotor to be 2,800 RPM, what is the slip of the motor in units of RPM? All right, so that brings us to the third equation in the useful equations bank here. That's this guy. All right, that's telling us what the synchronous speed of a motor would be. In other words, when the motor rotor is exactly following the magnetic field as it rotates around the stator from the input electricity. Okay, so we know that the rotor speed in this motor, where we've replaced the permanent magnet with a squirrel cage rotor, so we've turned it into an induction motor, equals 2,800 RPM. And 8. We know that slip is equal to, if we're doing it in terms of RPM rather than like a percentage or ratio or something like that, well then that's going to be the synchronous speed minus the rotor speed. All right, the difference in those 2 things. So what we need to do is find V sync, and we have an equation for that, and all of the parameters that we need. The equation looks like this. Poles per phase in the denominator, frequency times 120 in the numerator. And if we substitute in for the quantities that we've got here, 50 poles per phase, so we've got 1, 2, 3, 4, 5, 6 poles. Let's go back up there and count those. Right, for our definition of poles, and you can run into some alternate definitions where they do like they sort of roll all this poles per phase stuff together. You see that in engineering literature sometimes, a lot actually. But because we've been usually just associating poles with individual electromagnets, I stick with that with our equation. So all we really need to do is count up the number of windings here, and we've got 6. 1, 2, 3, 4, 5, 6. So we come back down here, we enter 6 for the number of poles, we enter 3 for the number of phases, because we're told that at the beginning of the problem, that's what we're doing. We've got in the numerator, we've got 6,000, right? So 100 times 50, 5,000, 20 times 50, yeah, 6,000. Okay, 6,000. And we divide that by 6 divided by 3, so 2. And so the synchronous speed is 3,000 RPM. And that means that if we come back over here, bring that down here, our slip is going to be, going off the bottom of the screen there, slip is going to be 3,000 RPM, and the rotor speed that we have been given in the problem that we measured it to be is 2,800 RPM. So the slip here is 200 RPM. Okay. So the difference in the speeds is, let's see, 200 revolutions per minute. And so you're talking about a few revolutions per second difference in the speed of these two things. And that's a pretty rapid, that's a pretty good clip. So you're going to have a rapidly changing magnetic flux, so number of magnetic field lines through all of your squirrel cage loops. And so you're going to induce quite a bit of current in the squirrel cage loops, and that gives you plenty of torque, hopefully, to turn whatever it is that is attached to your induction motor here. Okay, but 200 RPM is what we're looking for. Now, the next question. Consider an AC motor that has a permanent magnet on its rotor. Okay, so exactly like the toy one we discussed in lecture. So that's electromagnet, rotor with a permanent magnet on it, and then we need to hook up our electromagnets to an AC source and complete the circuit. Okay, great. Explain that why there would be no continuous rotation of the rotor if a DC source was accidentally connected to the stator. Okay, well, we know, right, that it requires AC, so that's sort of like the nominal, like, okay, well, we know it's not going to work. But the reason that it wouldn't work is that if you replaced your AC with a DC source, like a battery, well, then current would only ever flow in one direction. And so the magnetic field that these electromagnets create on the stator here, and that would be experienced by the rotor, would never change either, right? It would always be going this direction, same intensity, so same number of field lines, all that kind of stuff. And this rotor in this particular position would feel a torque, but only until it aligned with the magnetic field, like a compass needle, right? North and south. And once it's done that, it wouldn't feel any torque at all. And so you'd get maybe a little tiny bit of rotation, but no continuous, constant, clockwise rotation on your rotor, and that kind of defeats the purpose. So that's the walkthrough explanation. And the basic idea is DC equals constant voltage, which leads to constant current, which then leads to constant magnetic field. And that, in turn, means no torque, or at least no continuous torque on the rotor. So it'll make a pretty bad motor. Okay, number 3. Say that you were told that an induction motor was connected to an AC source, and has been for a long time, so it's just motoring along doing its thing, rather than like just starting up, like you just connected AC, and that the torque on the rotor is large. Okay, so that's the big piece of information that you're given here. You may assume that this is a normally functioning motor, nothing is broken, and has been constructed properly. What can you deduce about the current flowing through the squirrel cage bars? Okay, well, if you have large torque, we know from our discussion of, well, AC motors, but as well with DC motors, that if you have a large torque, that implies, right, from the Lorentz force, implies that if you have a large torque, you have a large force, and that means that you're going to have a large current. Okay? You need a big current if you're going to have a chunk of conductor that's carrying that current experience a big force and give you a big torque. Okay, so large torque implies large currents in the squirrel cage bars in our induction motor here. And that is the answer that we're looking for here, okay? So you would probably want to write out a little bit more than what I've done here, but hopefully the verbal explanation goes along fine with that. All right. So if you want a big force and a big torque, then you need a pretty large current. It's worth saying that the magnetic field here would be changing in the case of an AC motor, right? Because the current being fed into the electromagnets is changing, and so the field is changing. But it is changing back and forth between two limits, right? You're going to go from a peak to a trough to a peak to a trough to a peak to a trough. And so, though this is a variable, if you're just told sort of large average torque, it's going to be the current that is most strongly affecting that. And so we can just concentrate on that. What can you deduce about the rotor velocity in this motor? Well, let's think about that. You can't deduce anything super specific about it. It's not like you can say, oh, well, it's 0. Or, oh, well, it's equal to the synchronous speed or something like that. But you can definitely sort of put some bounds on it, some limits on it. So if we have a large current, that implies that we have a large induced voltage difference. All right. And how do we induce voltage differences? Well, we get them with Faraday's law, right? That's what we're doing. We're changing our magnetic flux, our number of magnetic field lines through all of the loops of the squirrel cage. So we're inducing a bunch of voltage so that we drive a whole bunch of current through those conducting bars. Okay, so if large induced voltage difference, right? So that's telling us about this. So then we know that this rate change of number of magnetic field lines is large. And how do we get rate? How does the magnetic flux change? How does the number of magnetic field lines change in an induction motor? Well, it's because there's this difference between the rotor speed, around, okay, and the speed of the magnetic field rotating, the synchronous speed, okay, that we can calculate and did calculate on the first question of this quiz, okay? So if this is large, if that is changing a lot, then slip, that difference between rotor speed and synchronous speed, must be relatively large. Okay. Otherwise, right, if you have tiny slip, then the rotation speed of the magnetic field and the rotation speed of the rotor are really close together, so there wouldn't be a very rapidly changing magnetic field, or rather magnetic flux, and then the rest of this wouldn't follow, okay? So sort of working our way back down through the logic. So slip must be large, and if slip is large, then the rotor speed is much less than the synchronous speed. All right. That's about all we can say with certainty. We can say that it's not anywhere close to synchronous speed. We wouldn't want to say that it's 0, because assuming that the motor is actually functioning properly and that we're not doing something too crazy like stalling it out with a really big mechanical load on it, like something it wasn't designed to turn, then, normally function, blah, blah, blah. So we wouldn't want to say that rotor speed is like 0. We would say it's relatively low, at least compared to the synchronous speed of the motor. But other than that, we can't say much without a lot more information. Okay, so that's the end of our review for the afternoon quiz. I'll probably post one more little video to supplement our knowledge of AC motors and give you a little bit more background on them. But the next video you'll see from me this week is going to be on, well, sort of leading up to simple radios. A little bit of background information, stuff that you might have covered a little bit in GMDSS, just depending on which professor you have and the emphasis this semester. But a little review of that, I suppose, can't go wrong. All right, so we'll see you then. Thanks for listening and viewing.